In this chapter, we're going to be going over limits and the derivative once again, just an extension of the last section. So in the previous one, we used limits to help define what the derivative is, and we'll see that again in a little bit. So let's start here with limit notation. So this is going to be the notation that we use when we are using limits, and we read it as the limit of f of x as x approaches a equals L, whatever the number L happens to be. This means that as x gets closer and closer to the x value of a, the corresponding y values, the corresponding function values, get closer and closer to L. Now, as x approaches a, if the values for f of x don't approach a specific number, meaning the left side and the right side are different, that means that the limit does not exist. And just a little side note here that we'll see, the function does not have to be defined at that x value in order for the limit to exist. So we're going to be finding this several different ways. We're going to be finding limits using tables, using graphs, and then algebraically using certain properties of limits. And let's go ahead and start by finding limits using tables. So in order to do this, what we're going to do is we're going to pick values to the left of a. So as you can see down here in this example, we have an x value approaching 2. So we pick values to the left of 2 that are getting closer and closer to 2. And then we also pick values that are greater than 2, but getting closer and closer to 2. So you can see that these are converging to 2 here in the middle. So we pick values to the left of 2, we pick values to the right of 2. We take those values, we plug them in the function, and get out their function values, their y values. And then we're going to see what does it look like these y values are approaching, and what it seems like it's getting closer and closer to, that's going to be our answer. Okay, let's go ahead and do this example. So we have our function. We want to find limit of 3x minus 5 as x approaches 2. And we have our x values to the left, x values to the right. So let's go ahead and plug those in. So let's plug in 1.99. So this box is going to be the function evaluated at 1.99. So 3 times 1.99 minus 5, that's going to give us 0.97. And next, let's evaluate f of 1.999. Plug that in the function, we get 0.997. Lastly, for the one to the left, plug in 1.9999, and we get 0.9997. So for the x values that we chose, we didn't have to choose these ones necessarily. We could have chosen maybe 1.9, and then 1.95, and then 1.99. Either way, it just has to be values getting closer and closer to our value of 2. Okay, so let's plug in ones from the right. Let's plug these in. I'll go ahead and just fill those in. And we get those values, so we plug those in just like we plug the other ones into the function and evaluate. So now we ask ourselves, what does it look like these values are approaching? Like, where does it look like they meet? And that's going to be our answer. Well, it looks like they're getting closer and closer to a value of 1, right? From both sides, 0.9997 and 1.0003. It looks like it is converging to 1. So that is actually going to be our answer. And you can see how it's kind of like a guess, but it's an educated guess. So the limit of 3x minus 5 as x approaches 2 equals 1. Because the y, that's where the y values seem to be going towards. Okay, so that's using tables. It's the same idea for every time you're using a table. And now let's jump over to finding limits using graphs. So we have 3 different graphs here. We want to find the limit as g of x approaches 2, or as g of x, the limit of g of x as x approaches 2 for all of these. So let's take a look at the first one for a. So it looks like as the x values are approaching 2 from both sides here, it looks like the y value is approaching 1. So that means the limit as x approaches 2 of g of x is going to be 1. Notice for this one that g of 1 or g of 2 does not exist because we have an open circle. So g of 2 does not exist, but the limit as x approaches 2 does exist. Okay, and next one for b here in the middle. We have this jump in the function at 2. So if we go from the left, if we start from the left of 2, and we start from the right of 2, those are approaching different values. Since those are approaching different values, one of them is approaching 2, the other one is approaching a y value of 1, that means the limit does not exist. Okay, and we typically can use the abbreviation DNE, it means does not exist. And then the last one on the right, we have 2. We can see it looks like there's some sort of vertical asymptote at x equals 2. So if we go from the left and we go from the right, they're both going towards infinity from that point. So what we could say is the limit equals infinity because it's approaching infinity from both sides of 2. Or sometimes you'll see that you can also say it doesn't exist. So for our sake, for right now in this class, we're going to say that either answer is acceptable. And once again, that's only because it has to do with infinity, positive and negative infinity. You can use that, or you can use does not exist. So now we're going to get into some evaluating some limits algebraically by hand. So let's start with two basic ones here. So two basic limits, we have the limit of c as x approaches a will always equal c. So that means, so c is a constant here. As it says right up here, it's some real number. And let's just see an example. Let's say we have the limit as x approaches 3 of 2. So based on this rule, our answer is going to be 2, right? But let's see what this means graphically. So 2 is our function in this case. So that means f of x equals 2. If we graph that, we have y equals 2 or f of x equals 2. That's just a horizontal line at y equals 2. And if we want to see what the y values are approaching when x is equal to 3, well, if we go to the left of 3 and go from the right of 3 and approach it, then it's obviously going to 2 because it's a horizontal line. So this answer is just 2. So just make sure you're not accidentally putting the x value as the answer. It's the function value, the constant function value. Okay, and the next one, we have the limit of x as x approaches a. That's always going to equal a. So it's going to equal a this time if this function is an x. And let's see an example, and let's see the graph just so we can see why. So we have, for example, let's have the limit as x approaches 2 of x. So based on this answer, we know the answer is 2 because that's what the x value is approaching. But let's see why. If we graph this, our function here is y equals x this time. We know that y equals x is a line with slope of 0, or slope of 1 and y-intercept of 0. So we have x is approaching 2, and we want to see what is the y value approaching. Well, it looks like the y value is approaching a y value of 2 also. So the answer is 2. And that's because this is the identity function. Each value has an output of itself, because it's y equals x, y equals the original value. Okay, so those are two shortcuts essentially. And now we're going to have some limit theorems here that are going to help us evaluate limits. So it's going to seem a little confusing for a second because we just have a lot written here, so bear with me. So we have the limit of f of x as x approaches a, the limit of g of x, assume that they both exist, and then we get these 6 different theorems. So if we have a constant, k, and we're evaluating the limit of k times f of x, what we can do is bring the constant out front and evaluate the limit separately and then multiply them together. And for the next one, if we have a exponent on our function, we're taking the limit of that, we can actually take the limit of the function, get an answer, and then raise that answer to the exponent. And then the next one, if we are adding two functions together in a limit, the limit of f plus g, we can do them separately, limit of f plus the limit of g, and then add the results together. Same thing with the one below with subtraction, limit of f minus g, do them separately, subtract their answer. It's almost like distributing in the limit. That's not technically what it is, but that's kind of what it looks like. And for the next one, we have the limit of f times the limit of g. Once again, do them separately, limit of f times the limit of g. And for the last one, we have the limit of f divided by g. Do the limit in the numerator, limit in the denominator separately, and divide your answers. So it's going to seem pretty obvious and pretty unnecessary to do the long way for these. So let's just go ahead and do a couple of these doing the long way, and then we'll get to an easier method. So for example, A here, we want to find the limit of x cubed as x approaches 2. So this is going to be an example where we can use that exponent 1. We can rewrite this as the limit as x approaches 2 of x. We can get an answer, and then we can cube the answer. So the limit as x approaches 2 of x, we know that that is just 2 based on the previous page. So our answer is going to be 2 cubed. So this answer is 8. So nice and easy. Let's see the next one. We want the limit of 5x cubed as x approaches 2. So this is going to start with that constant rule. 5 is the constant. We can bring that out front and do the limit as x approaches 2 of x cubed. We actually just did this portion, right? We just did the limit of x cubed. So this is going to be 5 times 8, because we just got 8 in this previous answer up here. So our answer is just 5 times 8, and we get 40. Okay, and then let's keep on building on that. We have the limit of 5x cubed minus 15. So this time we see subtraction. So let's go ahead and do it, give that limit to both of those separately. We want the limit as x approaches 2 of 5x cubed minus the limit as x approaches 2 of 15. So we give them both the limit because they were separated by subtraction. And now we can go ahead and evaluate them separately. We just found this one, the first one on the previous page. We just said that answer was 40. So it's going to be 40 minus the limit of 15 as x approaches 2. That's 15 is a constant, so that means our answer is just that constant 15. And then 40 minus 15 gives us 25. And two more here. We have the limit of the square root of 5x cubed minus 15. So we have to remember that the square root is an exponent, right? The square root is just an exponent of 1/2. So it's going to have that same exponent, that same exponent rule, where we can put the limit inside of it. So we can take the limit as x approaches 2 of 5x cubed minus 15, and then take the square root of that answer. So once again, we just did this in the previous question, and we got an answer of 25 for that limit. So this is just going to be the square root of 25. So our answer is 5. And we have one more, I believe, here. The limit of the square root of 5x cubed minus 15 over x to the 5th as x approaches 2. Since this is a fraction, we can give the limit to the numerator portion and the denominator portion separately. So we're going to do the limit in the numerator and the limit in the denominator. And the limit in the numerator is, once again, just what we got in the previous question. it was the limit of that square root. We got an answer of 5. And now we need to do the limit in the denominator. The limit of x to the 5th as x approaches 2 is going to be the same thing as if we do the limit first, get an answer, and then raise that answer to the 5th. So since that's that identity function, the answer is going to be 2. 2 to the 5th, we get 32. 2 times 2 times 2 times 2 times 2. And we get 32, so our answer is just 5 over 32. It doesn't simplify at all, so we can just leave it just like that. Okay, and now for some other helpful theorems. So kind of stringing together those theorems that we were just using, we can have these extra theorems that are going to be a lot shorter. So these theorems say that if your function is a polynomial function and you're taking the limit of the polynomial function, all you have to do is plug in that a value into the polynomial, and that's going to be your answer. And the same thing goes for if it's a rational function. Just plug your number in to the function. As long as it doesn't make the denominator 0, then you can just plug it on in and evaluate your answer. This is called the direct substitution property also. And it's going to make it a lot easier. We don't have to write out each one of those individual steps that we just did before. Okay, so let's go ahead and see this first example using a factoring technique. So let's let's evaluate the limit of x squared minus 9 over x minus 3 as x approaches 3. So notice that if we tried to plug this in, if we tried to use this direct substitution method, we would plug it in right away. We would actually get 0 over 0, right? So that means direct substitution does not work because it made the denominator 0. So even though this was a rational function, direct substitution should work for rational functions unless it makes the denominator 0. So what we're going to do is do exactly what it suggests up here, and we're going to factor it. So let's go ahead and I'm just going to rewrite it. The limit as x approaches 3 of x squared minus 9 over x minus 3. Typically, if you have a rational function and you end up getting 0 over 0, typically that's going to mean you can factor it. So we can factor the numerator, difference of squares, x plus 3 times x minus 3. And that denominator stays the same. Now we can cancel off a common factor of x minus 3. That leaves us with the limit as x approaches 3 of x plus 3. And now we can apply that direct substitution because now we can plug in 3. If we plug in our 3 now, we get 3 plus 3. And that gives us a value of 6. So the limit is x squared, the limit of x squared minus 9 over x minus 3 as x approaches 3 equals 6. So if we graph this, this would be a rational function with a hole when x equals 3. So f of 3 doesn't exist, but the limit does. So basically you want to simplify those as much as you can, and factoring is one of our most common techniques until you can do direct substitution. Okay, so now for one of the most important things actually that we're going to do, and for calculus in general, is the limit definition of the derivative. So we mentioned this in the last section with the difference quotient, but now we're going to use limit notation. So if the function is differentiable at x, meaning we can actually take the derivative and plug in the value for x, then we have this difference quotient, which once again the difference quotient is f of x plus h minus f of x all over h. The difference quotient approaches some number as h approaches 0, and this is the notation that we use. So same thing that we did at the end of last class's lecture, except a more formal definition. So the derivative as a limit is going to be f prime of x, the derivative of f, equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And sometimes it'll happen where the difference quotient doesn't actually approach any specific value. If that's the case, that means f is not differentiable or non-differentiable at x. So what we're going to be doing is we're going to be taking the derivative using this method with limits, and our goal is going to be to plug in a 0 into h because that's what h is approaching. We can't do it right away or else we'll be dividing by h. So we're going to have to simplify first and then simplify until we're able to plug in 0 in for h. So let's go ahead and see an example with a polynomial. We want to find the derivative of f of x when f of x is x squared plus 2x plus 2 using that definition above. So let's go ahead and write down the definition. And also notice we could take the derivative of all of this function, all three terms, using the power rule, which we already have learned, which is a lot easier, but we're going to do it this method. So we know that f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. And if you need a refresher on this difference quotient, take a look at last section's lecture material. So what we need to do, we only need to do one difficult thing. We just need to figure out what the heck f of x plus h is, because we already know what f of x is. It's just our function. So on the side, let's find f of x plus h. We're going to find that by plugging in x plus h into every x. So it's going to be x plus h squared plus 2 times x plus h plus 2. And we need to simplify this. X plus h squared, you might have to FOIL that out on the side. X plus h times x plus h, you should end up getting x squared plus 2hx plus h squared. I like to use the shortcut version for that and say it is the first one squared plus 2 times both of them together plus the second one squared. Okay, and then the next one we have to distribute 2, so plus 2x plus 2h, and then plus that last 2 at the end. So we actually can't even simplify that anymore, so we're done with that. Let's go ahead and substitute that in. Instead of x plus h, f of x plus h, we're going to have x squared plus 2hx plus h squared plus 2x plus 2h plus 2. And then it's going to be minus f of x. So now we just need to subtract our function and make sure we have parentheses. Our function is x squared plus 2x plus 2. And that is all divided by h. And also we can't forget to write the limit as h approaches 0 out front. So we need to keep writing that limit out front until we actually plug in 0 into h. So let's go ahead and simplify. So what I like to do is simplify from this step. You could write a whole nother step and distribute the negative. I like to skip that and start canceling. If f of x is a polynomial, which it is, then this whole entire f of x portion is going to cancel every single time. So we have x squared minus x squared. We have 2x minus 2x, and I'm saying minus because of that minus here in the middle. And then we have 2 minus 2. So all of those terms in the original f of x canceled out. Let's rewrite it. We have the limit as h approaches 0 of 2hx plus h squared plus 2h all over h. And then always remember that you're trying to plug in 0 into h, so that means that denominator has to go. And we'll notice that everything in the numerator has an h in it. So what that means is we can actually factor out an h in the numerator. We'd be left with 2x plus h plus 2, all divided by h. And now is the time when you realize you did everything correct. You can cancel off those h's, and we get the limit as h approaches 0 of 2x plus h plus 2. And now we can do that direct substitution and plug in 0 and get 2x plus 0 plus 2. We're plugging it into h. and we get 2x plus 2. So this is our derivative f prime of x. It is 2x plus 2. And just also notice here that if we have the derivative of a polynomial, the derivative of the polynomial is always going to be 1 degree less, meaning the highest exponent, 1 degree less than the original function. Now we're going to be doing the derivative of a rational function. So for this rational function, we want to find the derivative of f of x, which is 1 over x. So let's go ahead and use that same limit definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And let's figure out, actually let's go ahead and plug it right in right away because it's a little bit easier to plug this in here. So it's going to be the limit as h approaches 0. F of x plus h is just going to be 1 over x plus h. Plugged in the x plus h in for x, and then minus f of x. F of x is 1 over x, all divided by h. And just as before, we can't just plug in 0 into h because we'll be dividing by 0. So what we have to do in the numerator is actually get common denominators. So let's do that over here on the side just so it doesn't get too messy. So getting common denominators, that should be a plus or a minus. Getting common denominators here, we have to multiply the first one by x, the second one by x plus h. We're multiplying each one by the other one's denominator. So that's going to give us x over x times x plus h minus x, we don't need that parenthesis, minus x plus h over x times x plus h. We can combine these and get x minus x plus h over that common denominator. And we can realize that the x's actually cancel, right? We have x minus x. Distribute that negative, but I'm just going to skip writing that step. The x's cancel. We end up getting negative h. And this is as far as it can go for now. Okay, so let's go ahead and just substitute that into the numerator. That's what the numerator becomes. So the limit as h goes to 0 of negative h over x times x plus h over h. So we still need that denominator to cancel, but the good news is that it's about to. Let's do some keep, change, flip. Let's keep the numerator the same, or this big numerator the same. And let's change the multiplication and reciprocate the h in that denominator. Now we can see that these denominators cancel, and we are going to be left with the limit as h approaches 0 of negative 1 over x times x plus h. And we go ahead and we plug in 0. That's negative 1 over x plus, or x times x plus 0, which gives us negative 1 over x times x, which is negative 1 over x squared. So that means the derivative of 1 over x is negative 1 over x squared. Okay, and now for the next example, it's a function with a radical. And our function here is f of x equals the square root of x. And we're using this same definition, the limit definition of the derivative. And this one is going to be an easy one to plug in, so let's go ahead and do that. F of x plus h is just going to be the square root of x plus h minus f of x, square root of x, all over h. So for this one, you have to know what to do for this one. It is a little bit tricky. We need to know to multiply by the conjugate of the numerator in this case. Okay, so anytime you have two terms and there's at least one square root, more often than not, you're going to need the conjugate. So the conjugate of the numerator is x plus h plus the square root of x. Multiply that in the numerator and denominator. And what we end up getting, let's use the shortcut version for conjugate multiplication. That's a plus b times a minus b equals the first one squared minus the second one squared. or you can FOIL it all out, but it's going to get messy. So let's have the limit of, as h goes to 0, of that whole entire numerator is the conjugate. So the first one squared is going to be the square root of x plus h squared. I'll just write this out for now. Minus the second one squared, which is the square root of x squared. And then that whole denominator, we're just going to leave it alone for a second. H times that conjugate. And then let's just see what happens here. The numerator, if we are squaring a square root, they cancel off. So we're just left with x plus h minus x. And notice that I'm not distributing that h in the denominator. We're going to need that in a second. The numerator, the x's cancel. X minus x. So we get the limit as h goes to 0 of h over h times square root x plus h plus square root of x. Now the h's cancel, so we're good to go. We have the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. And now we can plug in 0 here. So plugging in 0, we have 1 over the square root of x plus 0 plus the square root of x. And that's going to be, I'm just going to move this up a little bit. And that is going to be 1 over the square root of x plus the square root of x. So that gives us 1 over 2 radical x, because we add them together, just like x plus x is 2x, square root of x plus square root of x is 2 square root of x. So this is our derivative, f prime of x. Okay, so what we can do actually is extend that definition, that limit definition of the derivative, if we want to evaluate the derivative at a certain value. We could always just find the derivative like we just did and then plug in the value here. That'll work completely fine. But we can skip that by using these steps here. So first, we're going to write the difference quotient in this form, because a here is going to be a number. We're evaluating f prime of a. So we're going to write the difference quotient in this form. Essentially, instead of an x, we're plugging in a into x, which is going to be a number. Then we're going to simplify it as much as we can, and then find the limit as h goes to 0, and that's going to be f prime of a. Okay, so let's go ahead and see this example. We have f of x is 15 minus x squared, and we want to find f prime of 5. So what we're actually going to be doing, I'll write it out here, and I'll go back and write it out up here also. It's just the same difference quotient limit definition of the derivative, except we're just using a instead of x. So what we are going to do is we recognize that our a value is 5, right? So we're finding f prime of 5. So that's going to be f prime of 5 equals the limit as h approaches 0 of f of 5 plus h minus f of 5 over h. And let's evaluate both of those on the side. Let's do the easy one first. F of 5 is just the y-coordinate, 15 minus 5 squared, which is 15 minus 25, so negative 10. And next, let's find f of a, or 5 plus h. And that's going to be 15 minus, instead of x, we have 5 plus h squared. And let's go ahead and simplify this. So 15 minus 5 plus h squared is going to be 25 plus 10h plus h squared. So I just use the shortcut method for that, or you can FOIL it out on the side. If we distribute that negative in combined like terms, we're going to get negative h squared minus 10h, and then 15 minus 25 minus 10. I just switched the order so it looked a little better. And let's go ahead and plug those in. So f of 5 plus h is that whole negative h squared minus 10h minus 10. minus f of 5 is negative 10 all over h. And we can see here that the negative 10 minus negative 10 will cancel. And then we have, essentially everything has an h in it now. We have negative h squared minus 10h all over h. We still can't plug the h in, so what we have to do is factor out an h in the numerator. And we factor out an h, we're left with negative h minus 10 all over h. And now we can cancel that h in the denominator, which is what we wanted. And we get the limit as h approaches 0 of negative h minus 10. We plug in a 0 into h now, so that's negative 0. I'm not going to write negative 0 because that's not a number and that looks weird. 0 minus 10, so we get negative 10. So that means that f prime of 5 equals negative 10. So that means the slope of the curve at x equals 5 is negative 10, or the slope of the tangent line at x equals 5 is negative 10. Okay, and let's do one more of these ones. And we're still evaluating f prime of 5 here. So let's write down the definition. We have our limit definition where we're plugging in our value of a for 5 into a. So let's do that on the side. Let's find f of 5. F of a is f of 5. And actually, let me write down what we're actually doing first. Let's plug in a 5 everywhere there's an a. And we get that form. So we're finding f of 5. We plug in a 5 into the function. That's 1 over 2 times 5 minus 3. That gives us 10 minus 3, so 1 over 7 for that denominator. And we have f of 5 plus h. We plug that in. That's going to be 1 over 2 times 5 plus h minus 3, so it's a little messier. And let's go ahead and simplify that. I'm just going to do it in one step. Distribute the 2. We get 10 plus 2h minus 3. 10 minus 3 is 7, so 7 plus 2h, or 2h plus 7, whatever you prefer. Okay, let's go ahead and plug these in here. So it's going to be the limit as h approaches 0 of f of 5 plus h, which is 1 over 7 plus 2h, minus f of 5. F of 5 is 1 over 7 all over h. So obviously we can't plug in a 0 into h yet because it's in the denominator. So it looks like we're going to have to get some common denominators in the main numerator. So getting a common denominator, it looks like maybe let's do this on the side, make it a little bit cleaner. If we're adding 1 over 7 plus 2h, or if we're subtracting minus 1 over 7, that means we have to multiply the first one by 7 over 7, and the second one by 7 plus 2h over 7 plus 2h. So once again, just multiplying each term by the other term's denominator. That's going to be 7. I'm just going to combine this all at once. They're going to have the same denominator of 7 times 7 plus 2h, minus, for the numerator, we have 7 minus, parentheses, 7 plus 2h times 1, so it's just 7 plus 2h. So I just skipped the step of writing down the intermediate step, and now let's simplify this. We can simplify this because distribute the negative. 7 minus 7 is 0, and then we get negative 2h over 7 times 7 plus 2h. So it's definitely really messy, and it doesn't seem like anything good's going to happen, but things will cancel. That's going to be the numerator. So let's plop it on in. And this is still over h. And what we can do is keep, change, flip once again. We keep, I'm going to write it right up here. We keep the original numerator the same. Reciprocate that, or change the multiplication and then reciprocate that denominator. And now we see that the h's cancel and we get negative 2 over 7 times 7 plus 2h. So that is nice because now we can actually plug in 0. So let's just rewrite it. We have the limit as h approaches 0 of negative 2 over 7 times 7 plus 2h. And we plug in 0 now. And that gives us negative 2 over 7 times 7 plus 2 times 0. That's going to give us 7 times 7 in the denominator. So we get negative 2 over 49. So that means f prime of 5, the derivative when x equals 5 is negative 2 over 49. And definitely a lot messier for that one. Okay, and then the last concept for this section is limits involving infinity. So let's say we have this function that's shown right here, and let's notice that as x is getting larger and larger and larger, the function value is approaching 2, right? It's getting closer and closer to 2, which we actually say it's getting asymptotically close to 2. So what we would say in this case is that the limit, that 2 is the limit of f of x as x approaches infinity. So the way that we would write this is the way that we usually write it. The limit of f of x as x approaches infinity equals 2. So a little bit new notation here because x is approaching infinity instead of an actual value. And then we can have it the other way also if we have this graph and we see that x is getting more and more negative, further and further to the left. It looks like that function value is approaching the x-axis, which means it would be approaching a y value of 0. So in this case, we would say the limit of f of x as x approaches negative infinity, because it's going all the way to the left, equals 0. And let's see a couple examples by hand just so we can see how we do this. So if you notice, these are actually horizontal asymptotes. If this happens, these are horizontal asymptotes. And if you remember about rational functions and how to find horizontal asymptotes, that will come in handy, but I'll mention that again in a second. So we want the limit of 1 over x squared plus 1 as x goes to infinity. So the way that we solve this one and the way that we're going to do it is solely based on the fact that it's going to positive or negative infinity. We're going to divide every term by the variable with the largest exponent. Okay, and then we'll do it this long way. It's not too long, and then we'll kind of do the common sense way here. So we have the limit as x goes to infinity. The largest exponent is x squared, so we're going to divide everything by x squared. X squared divided by x squared plus 1 divided by x squared. So we can do this. We can do this because we're doing it to the numerator and denominator, so we're not actually changing anything. And let's go ahead and simplify this a little bit. The limit as x goes to infinity of 1 over x squared over 1 plus 1 over x squared. So it looks like we just made this messier, right? But actually what we just did is pretty helpful. And we need to use this little fact that I wrote over here. The limit as x goes to infinity of 1 over x to an exponent will equal 0 when that exponent in the denominator is either 1, 2, 3, 4, 5, or and so on as a natural number. So let's take a look at these separately. This is going to be equal to the limit. We're going to put the limit in the numerator. And then we're going to put the limit in the denominator with each term in the denominator. So the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 1 over x squared. Okay, so now we're going to evaluate these separately. The 1 in the numerator equals 0. So as x goes to infinity, 1 over x squared is going to 0, and that is based off of what I wrote down right here. And then the other one, the limit for 1 is a constant, so it's 1, plus the limit of 1 over x squared as x goes to infinity is 0. So this is equal to 0 over 1. So this whole entire limit is equal to 0. Okay, so let's go back up and mention two things here for shortcuts. The shortcut is the horizontal asymptote idea with a rational function. If the degree in the denominator is larger than the degree in the numerator, then the horizontal asymptote will be at y equals 0, which is what the limit is in this case. And also let's think about it as x for this function. As x is getting larger and larger and larger, that denominator is going to get that denominator is also going to get larger and larger and larger. If the denominator of a fraction is getting larger, the number as a whole is getting smaller and closer to 0. So hopefully that kind of just logically makes sense what is happening as well. Okay, let's do one more here, and then I'll mention the shortcut. So we need to, the limit of 6x minus 1 over 2x plus 1 as x goes to infinity, we need to divide everything by the largest exponent, which is going to be just x. So let's do 6x divided by x minus 1 over x. Everything gets divided by x. Over 2x over x plus 1 over x. And let's go ahead and do these separately. So the way that I like to do it is, let's simplify it first. Simplifying the numerator, 6x over x is 6 minus 1 over x. 2x over x is 2 plus 1 over x. So instead of writing the limit in each one and wasting time, recognize that these two will both approach 0 because it's 1 over x based on the definition that I wrote above. That will approach 0 as x goes to infinity. So all we are left with is the limit for 6 over 2. Those are both constants, so our answer is just 6 over 2, which is 3. Okay, so that wasn't as bad. The shortcut for this one is it's another horizontal asymptote shortcut, is if the degree in the numerator equals the degree in the denominator, they're both an exponent of 1, the horizontal asymptote is going to be the ratio of the leading coefficients, which in this case is 6 divided by 2, which is 3. So that is another super nice shortcut for this one. So I just kind of wrote it in over here on the right and summed it up. These are the shortcuts for horizontal asymptotes. Degree of the numerator is less than. Oops, that shouldn't say less than or equal to. That should just say less than. So if it's less than, the degree of the numerator less than the degree of the denominator, that means the horizontal asymptote at y equals 0. That was like the first example we did right above. If the degree of in the numerator and the degree of in the denominator are equal, that means it's y equals the ratio of the leading coefficients. That's the one that we just did right now. If the numerator degree is larger than the denominator, then there's no horizontal asymptote. So the answer that we're essentially finding right here is the horizontal asymptote. Okay, so that is it for this section.